The most natural and obvious way to get a dual pair is to take a linear programming relaxation of our integer program and then take the dual of that. Before we go ahead and do this obvious technique, first let's talk about what the linear programming relaxation actually does for us. We saw in previous lectures that the linear programming solution, or our linear programming relaxation, is an upper bound or a dual bound on the optimal solution of our integer program. This is fantastic. However, in order to get this dual bound, we need to solve this linear programming to optimality. Sometimes solving a linear program to optimality can take quite a bit of time. If we had some alternative over here, where instead of solving something to optimality, we could just take any feasible solution and have that feasible solution be an upper bound, we would be in better shape computationally. That's why we're going to take this dual bound. So to take the dual linear program, we go through the standard technique. We'll have our linear programming relaxation. We multiply every constraint by a variable, and then we manipulate this algebraically until we get to the dual. This is the dual program, the dual linear program. And now it has even a more special function of being a dual bound to an integer program, the integer program associated with our linear programming relaxation. The important point of this dual is that any feasible solution is going to provide an upper bound. So if I were to take some u tilde, that's a feasible solution, and I evaluated the objective function at this feasible solution. So I look at the sum over all j of bj u tilde j. This is going to be an upper bound on the optimal solution to this dual linear program. We can see how this is going to help us when we're looking at our original integer program. We know that the value of our linear program is equal to the value of our dual program. This comes from duality theory for linear programs. We also know that the linear program is a relaxation of our integer program, so ZLP is an upper bound on Z star. A consequence of these two is that our linear programming dual, our dual linear program, is an upper bound on the original integer programming solution Z star. And now, because of this feasibility, any feasible solution, and in particular this feasible solution u tilde, is also going to provide an upper bound on our original Z star. This is going to be true for any dual feasible solution. So if we have a dual feasible solution, it's going to provide an upper bound to the value Z star. The key point here is that we don't need optimality. Instead, we can take any feasible solution, and a feasible solution will suffice as our dual bound. Computationally, this gives us quite a bit of power. Now we can put the pieces together and show that our dual linear program and our original integer program form a dual pair with one another. Here we have our integer program. We've taken its linear programming relaxation, and we know that the linear programming relaxation is an upper bound on our integer program. We've also taken the dual linear program, and we know that the dual linear program is equal to the value of our linear programming relaxation. We'd like to show that our dual linear program over here is going to form a dual pair with our integer program over here. The way we're going to do this is first note that the feasible set of points inside of our integer program is a subset of the feasible points inside of our linear programming relaxation. We also know that CTX, the objective function value of our linear program, is going to be at least equal to BTU, the objective function value of our dual linear program. And this is going to be true for all x in the polyhedron P and for all u in the polyhedron U. This again comes from linear programming duality theory. These two together imply that CTX is going to be greater than or equal to BTU for all x in X and for all u in U. The only thing we're going to change here is replacing u with P, or rather replacing P with X. Here, X is a strict subset of P, so because this statement is true, clearly this statement should be true. We're just taking a smaller set. Because of this is exactly the definition of what a weak dual pair is. So Z star and Z of our dual linear program form a weak dual pair. Because the operations involved here are really just taking the dual of a linear program and taking a linear program in relaxation of an integer program, we're not going to go through any examples.